build a closed-loop feedback optimization pipeline. This pipeline allows the AI to compile, execute, evaluate, and calibrate synthesis parameters programmatically. The architecture diagram. Mariitzi that compares the generated output, Karadika X synthesis.wav against the target, test ana wav tata. Mel sepstral distortion, MCD, the standard metric for voice synthesis closeness, dynamic time warping, DTW, to align phoneme duration mismatches so we can compare spectral envelopes at matched boundaries, spectral parameters. 3. Evaluates the MCD score. 4. Iterates until the synthesized voice converges to the target 11 Labs sound signature. And 3. Dynamic memory storage. Interface for coefficients. Currently, voice latent coefficients are hard-coded in the front end and solidity files. We need a JSON storage registry, e.g., config speaker profiles.json, containing dynamic coefficients, an upgraded C controller that loads these coefficients dynamically at runtime instead of relying on hard-coded parameters. As action plan. Step 1, create a Python. Acoustic alignment evaluator, create a Python script, scripts, voice aligner.py, that loads 2 WAV files, performs DTW, and computes the MCD. Step 2, integrate evaluator with the node server. Expose a new API endpoint, API optimize voice, that accepts a set of candidate weights, synthesizes the audio via the C controller, runs the MCD evaluator, and returns the metric. Step 3, implement the optimization loop. Build a wrapper script that runs the optimization loop in the background and writes the optimized weights to the contract or local config. To enable the AI to autonomously monitor, develop, and optimize speech synthesis routines toward matching the 11 Labs ANA reference sample, we need to build a closed-loop feedback optimization pipeline. This pipeline allows the AI to compile, execute, evaluate, and calibrate synthesis parameters programmatically. Thrusker architecture diagram. What needs to be built? That compares the generated output, Karadika CCEE synthesis.wav against the target, test ana wave. Mel sepstral distortion, MCD, the standard metric for voice synthesis closeness. Dynamic time warping, DTW, to align phoneme duration mismatches so we can compare spectral envelopes at matched boundaries. Spectral convergency, loss, to measure overall spectral curve match. 2. Auto-tuning optimization loop, an optimization script, e.g. using genetic algorithms or Bayesian optimization, that 1. Generates candidate speaker latent coefficient vectors, 9-dimensional reflection coefficients. 2. Invokes tests test speech CT controller with the parameters. 3. Evaluates the MCD score. 4. Iterates until the synthesized voice converges to the target 11 Labs sound signature. 3. Dynamic memory storage interface for coefficients. Currently, voice latent coefficients are hard-coded in the front end and solidity files. We need a JSON storage registry, e.g. config speaker profiles.json, containing dynamic coefficients. An upgraded C controller that loads these coefficients dynamically at runtime instead of relying on hard-coded parameters. Sutter's action plan. Step 1. Create a Python. Acoustic alignment evaluator. Create a Python script, scripts-voice aligner, PI that loads 2 WAV files, performs DTW, and computes the MCD. Step 2. Integrate evaluator with the node. Server, expose a new API endpoint, API optimize voice, that accepts a set of candidate weights, synthesizes the audio via the C controller, runs the MCD evaluator, and returns the metric. Step 3. Implement the optimization loop. Build a wrapper script that runs the optimization loop in the background and writes the optimized weights to the contract or local config. Closed-loop speech synthesis optimization plan. To enable the AI to autonomously monitor, develop, and optimize speech synthesis routines toward matching the 11 Labs ANA reference sample, we need to build a closed-loop feedback optimization pipeline. This pipeline allows the AI to compile, execute, evaluate, and calibrate synthesis parameters programmatically. The architecture diagram. You under what needs to be built. 1. Acoustic evaluation and similarity metric suite. We need a command line tool, preferably Python utilizing Librosa, SciPy, or C using FFT, that compares the generated output Karatka CK synthesis.wav against the target test ANA.wav. Mel sepstral distortion, MCD, the standard metric for voice synthesis closeness. Dynamic time warping, DTW, to align phoneme duration mismatches so we can compare spectral envelopes at matched boundaries. Spectral convergency loss, to measure overall spectral curve match. Later 2, auto-tuning optimization loop, an optimization script, e.g., using genetic algorithms or Bayesian optimization that 1. Generates candidate speaker latent coefficient vectors, 9-dimensional reflection coefficients. 2. Invokes tests test speech cat controller with the parameters. 3. Evaluates the MCD score. 4. Iterates until the synthesized voice converges to the target 11 Labs sound signature. 1. 3. Dynamic memory storage. Interface for coefficients. Currently, voice latent coefficients are hard-coded in the front-end and Solidity file. Shige. TSFI firmware, architectural supremacy over legacy OS paradigms. The TSFI firmware architecture has achieved empirical validation of its exponential efficiency gains compared to legacy standard libraries and runtimes like Node.js or glibc. By establishing a zero-copy, hardware-aligned foundation, the system completely bypasses the traditional bottlenecks of OS process management and system call translation. Based on today's rigorous benchmarking against standard PTY implementations, Node PTY, glibc forkpt, the TSFI firmware's efficiency 1. Creation and execution overhead 9.1x faster. Standard toolchains rely on fork or forkpt to spawn processes, incurring massive kernel overhead for page table duplication and TTY line discipline negotiation. By utilizing TSFI raw clone with strictly aligned 64 KB user space stacks, TSFI thread creation operates 9.1x faster. This empowers the firmware to spin up hundreds of concurrent background tasks, such as build watchers, language servers, or MCP workers, in under 6 milliseconds. Maintain load explicit, atomic store explicit, over 64-byte aligned mapped memory. Data transfer achieves 5145.16 EDABIS compared to 14098.70 MBSS for POSIX pipes, realizing a at 3.6's increase in bulk throughput. The CPU simply streams memory at raw DDR bandwidth. As 3. Absolute kernel, bypass for control logic. Legacy tools rely on the kernel to route signals, like sig-winch for window resizing or segint for interruptions, and to manage terminal states, to set ATR. This introduces measurable latency, e.g., 0.74 mins to 2.52 mins per operation, and synchronization risks. The TSFI firmware maps these states directly into shared memory matrices. Adjusting terminal size or line discipline flags is achieved via a single atomic pointer swap, registering latency. Tool state machines can transition instantly without yielding to the OS, such as asynchronous network polling, file I/O, or GPU compute, is securely injected directly into the TSFI event loop. We have proven that the TSFI firmware provides a mathematically deterministic, zero-leak framework, capable of absorbing and completely superseding the legacy Gemini CLI ecosystem with absolute structural superiority. 3D rendering advancements, DeepSeek and soft diffusion. Modern high-performance rendering architectures have evolved beyond the physical limits of raw polygon rasterization. Rather than relying on slow real-time ray tracing or heavy ML neural models at runtime, advanced systems leverage an ahead-of-time AOT tri-model compilation matrix, combining vision language models, DeepSeek coder, and stable diffusion to synthesize photorealistic geometry. This document details the transition from early 3D wireframe pipelines to hybrid neural procedural rendering, focusing on phase 0 offset matrices, VLM bounding box discovery AI, and soft diffusion texturing. Style 1, the tri-model AOT compilation pipeline. To achieve low latency real-time rendering, heavy neural models are decoupled from the active frame loop and move to the offline compilation stage. TSFI firmware architectural supremacy over legacy OS paradigms. The TSFI firmware architecture has achieved empirical validation of its exponential efficiency gains compared to legacy standard libraries and runtimes like Node.js or glibc. By establishing a zero-copy hardware-aligned foundation, the system completely bypasses the traditional bottlenecks of OS process management and system call translation. Based on today's rigorous benchmarking against standard PTY implementations, Node PTY, glibc, forkpty, the TSFE firmware's efficiency is characterized across 3 foundational domains. 1. Creation and execution overhead, 9.1x faster. Standard toolchains rely on fork, or forkpty, to spawn processes, incurring massive kernel overhead for page table duplication and TTY line discipline negotiation. By utilizing TSFI raw clone with strictly aligned 64 KDB user space stacks, TSFI thread creation operates 9.1x faster. This empowers the firmware to spin up hundreds of concurrent background tasks, such as build watchers, language servers, or MCP workers, in under 6 milliseconds, maintaining total virtual memory space coherence without thrashing the kernel scheduler. 2. Zero copy data. Throughput, 3.6 cat faster. Legacy IPC inter-process communication, like POSIX pipes, requires continuous read and write syscalls, endlessly shifting data between user space and kernel space. The TSFI firmware connects tools directly using LaWireLog ring buffers. By executing atomic operations, atomic load explicit, atomic store explicit, over 64-byte aligned mapped memory, data transfer achieves 51,045.16 by S, compared to 14,098.70 MBS for POSIX pipes, realizing a 3.6 per hours increase in bulk throughput. The CPU simply streams memory at raw DDR bandwidth. Unerschuer 3, absolute kernel. Bypass for control logic legacy tools rely on the kernel to route signals, like sigwinch for window resizing or isigint for interruptions, and to manage terminal states, tc-sita-titatar. This introduces measurable latency, e.g. 0.74 ms to 2.2 minutes per operation, and synchronization risks. The TSFI firmware maps these states directly into shared memory matrices. Adjusting terminal size or line discipline flags is achieved via a single atomic pointer swap, registering Natursta or latency. Tool state machines can to prevent anonymous or unverified logic execution inside the ancient core. The system-wide gate has been extended to validate the source of all instructions targeting CICS. Source 1, default reject gating. Under the default reject posture, EDSAC holds absolute authority over packet routing. Subsystems, including CICS, have no direct or default access to the instruction compiler delay lines. Every incoming instruction stream must prove its origin before it can be paused or executed. Uprooter 2, SSA registration check. During the CICS execution cycle, Ancient SDK CSITES on exec. The system intercepts the caller's ID, writer, ID, resolution pathway. The analyzer forwards the writer ID to the material to cloth bridge. The bridge attempts to resolve a corresponding character entity name, e.g., teddy bear scale character, or ancient federal worker character. SSA verification. This document reviews the inaugural issue of Dr. Dobbs' Journal of Computer Calisthenics and Orthodontia. Vulner 1, number 1, January 1976, focusing on code samples, such as Dennis Allison's 16-bit binary to decimal conversion routine, and Whipple and Arnold's Tiny Basic, TBX, and demonstrates how these retro optimization principles translate to the EVM YOL environments. Laris 1, Key Code Contributions and Architectural Alignment. Dr. Dobbs' issue, Year 1, Code, Concept, Original, 1976 Technology, TSFI2 Target Subsystem, Implementation Translation. For 16, Bit Binary to Decimal Conversion, Dennis Allison, Reciprocal Multiplication by $0.1, $110, to perform fast division and remainder calculation on the Intel 8080. EVM YOL utility functions. Optimize base 10 string formatting routines without slow arithmetic division cycles. Tiny Basic Interpreter, TBX, PCC. Minimalist bytecode interpreter with a 15 instruction intermediate language, IL. XEMM VM instruction decoder. Compact bytecode parsing and virtual program counter dispatch loops. Dr. Suding's calculator chip interface. Offloading complex math, sine, cosine, log, to external calculator chips via I/O. Coprocessor precompiles. Delegating heavy cryptographic and transcendental computations to EVM precompiles or host thunks. 2. Dennis Allison's reciprocal division algorithm 110. On early microprocessors like the Intel 8080, hardware division did not exist, and iterative subtraction was slow. Dennis Allison introduced a routine that calculated N das $10 by. This document provides a detailed technical analysis of the computational mathematics presented in the inaugural issue of Mathematical Tables and Other Aids to Computation, MTAC, January 1943. It explores the transition from hand-calculated tables to digital lookup tables, LUTs, and how it applies to low-level virtual machines like the ZMM. Doffer 1, the role of tables in early computation. Before electronic computers, mathematical calculation was bound to printed tables of logarithms, trigonometric ratios, Bessel functions, and probability integrals. The errata problem. Because these tables were calculated by human computers using pen and paper, they were riddled with printing and calculation errors. Much of MTAC issue number 1 was dedicated to listing errata for widely used engineering tables. Interpolation. When a required value fell between two table entries, computers used differences, method of differences, and polynomial interpolation, such as Newton's or Lagrange's formulas, to approximate the intermediate value. LabRef 2, Low-Level VM Optimization, Sine Lookup Tables, LUT. This document details the historical context of Cloud Learning Source, Inc., and outlines the integration blueprint for emulating their flagship product, HomeTax, as an on-chain YOL tax calculation and compliance coprocessor for the TSFI2 platform. LabRef 1, Historical Context, Learning Source, Inc., and HomeTax. Learning Source, Incatica, active in California during the early 1980s, was an ambitious home software publisher and retail computer pioneer. Their defining software product was Home Tax, the CP/M C64 software lifeline. Originally compiled for CP/M-compatible Commodore 64 architectures, Home Tax was one of the first home computer programs designed to guide users through the complex IRS Form 1040 layout using an interactive question and answer dialogue. Hotline. Support. Learning Source, Inca, innovated by offering a toll-free 800-number support hotline and periodic calculation updates for a small subscription fee. ERS Review. The program received positive recognition from the accounting firm Pricewaterhouse and a benign nod from the IRS, establishing a precedent for automated consumer tax compliance. DUP2, on-chain home tax coprocessor memory map, D6L, D6F. To mirror the consumer financial calculation logic of home tax at the protocol level, we introduce a YOL-based home tax compliance engine.
This document details the hardware mapping, register layouts, and software hooks required to bridge retro basic and machine language applications from Ahoy! Issues 7, 8, and 9 to our simulated 6502 YUL CPU, CPU 6502.YUL, and peripheral contracts. This document analyzes the engineering and physical principles presented in Elector Issue Number 2, January-February 1975, and Elector. This document provides a detailed technical analysis of Wallace J. Eckert's paper, Mathematical.
This document provides a detailed technical analysis of the engineering and physical principles presented in Electronica Verald Issue Nr. 16, January 1964, focusing on how component temperature modeling and radioactive half-life decays help us stabilize clipping responses in the.
In amateur radio, especially during the era of 73 magazine and high stability, we have successfully integrated high-end physically based shading, organic shape morphs, spotlight gradients, soft drop shadows, procedural color palettes, and cellular fur shell rendering with analytical soft shadows and directional ambient occlusion. Rendered viewport and parameter palette below is the output exported directly from the compiled application, featuring 1. Tapered cellular fur fibers. Fine hair strands generated using domain warped 3D cellular noise, tapering towards the tips, outer shell layer, and combed with gravity-based vertical groom and sine-based curl. 2. Directional ambient occlusion. Evaluated using adjacent ellipsoid distance checks, projected onto the surface normal and light direction. 3. Analytical soft shadows. High-fidelity soft shadows computed using ray ellipsoid distance field estimation. 4. Bilateral noise symmetry. Mirrored noise coordinate mapping around 0 point to ensure structural and lighting balance. Mar Teddy Bear rendered viewport, Jartje Home, Mariara Hell, Dutch Gemini, Anti-Gravity, Clyde Dada. The integration of the Dysnomia VM and the Unified Visual Compositor represents a milestone in ancient wavelet storage paradigms. By combining 6502 ROM emulation with modern dynamic memory-mapped register modifications, the system enables real-time vector coordination overlays directly atop low-level firmware. Dynamic NPC strategies. In ancient hardware routing structures, NPC behavior rules must remain unified to fit within the small binary constraints of physical cartridges. One, adversarial hunter droid, S1, uses proximity-weighted vector-seeking behavior targeting both active player ships and helper beacons to disrupt keycode transmission patterns. 2. Orbital mine is executed via a constant trigonometric orbit loop, utilizing a cosine radial pulse representing physical field effect transistor FET discharge cycles. 3. Helper droid, 3Cs, an autonomous inter-op unit programmed to shadow player coordinates, maintaining a target distance while balancing shield dynamics, and injecting Winchester MQ keycode structures. Synthesizer interface controllers, modern C64 cartridge. Titel. An den durchlüchtigsten Fürsten und Herren, Herrn Philippen, Landgraf in Hessen, von der Fürsichtigkeit Gottes. Ein Büchlin in Latin, beschrieben durch Meister Huldrych Zwinglin, vertütschet durch Leo Jud, dem Christliche durchluchtigest. Fürstenchen Jurchan, Wand Herrn Landgraf in Hessen, wie wohl keine Bucher der etwend, jenst vom dem, gelehrt allenthalb et zur Lobis, eine keine, Gottes gesund, sina kilchend, fussgond, verachtet dich. Fend werdet die sollend durch mit eine sundert flüssig Ohr dich entfond hochstetet. No Mike's objective. Securing the physical boundary logic of the Wayland window allocation inside the unified test main integration .seek-C testing suite, preparing for the firmware 1.0.0 phase 1 release. The mandate requires the testing structure to execute 100% of the firmware natively with zero operational divergence. RAF, architectural maintenance. We began by binding the open window and close window directives to the test main integration.c framework. A critical divergence was observed where the Wayland dispatch sequence failed to hold visual focus during the testing window. This was rectified by mapping a deterministic 200 frame epoch cycle via WS step safety epoch, enforcing a 10 ms frame dispatch wait interval. The window execution correctly initialized, negotiated the compositor, mapped the DMA buff feedback listener, and rendered 180 verified frames. However, the teardown sequence immediately triggered an AB316 structural violation segmentation fault within LAO registry find. Not resolving registry corruption. The physical memory logger law report memory to log was upgraded to dump comprehensive telemetry regarding active memory allocations, tracking execution bounds with exact file ICHIS and Hull-Heinel coordinates, explicitly segregating low-type wired, low-type basic, and low-type GPU states. The advanced logging system was forcefully shifted to the very beginning of law final or cleanup. Under status, honored fully qualified, verified, date, Tuesday, June 9th, 2026. Compliance checklist. Brand and separated game subsystems, Historical Ahoy, Issue 33, Blakemore 1986, and Commercial System 3 1987, Profiles Isolated and Selectable, Isometric Projection Correctness, Standard 3D, Titex Watch IZ, Right Arrow to Text D, SX, Wire Translation Math Verified, or D, Z Sorting Pipeline, Custom Memory Depth Sorting Algorithm Validated under High Concurrency, Yield Bare Metal Performance Target, Benchmark Throughput exceeded 78 text meets projections compiler strictness. Zero warnings, errors compiled under Wall, Wextra, Wera, C11. Memory sanitization. Checked against memory leaks on emulator teardown. Two, benchmark verification, metrics. Branches, test suite, bench-tuned system 3. This document details the procedural texture coordinate generation, TextGen, standard USD material previews, and visual styling used to achieve a soft, furry felt texture on the teddy bear and its sewn red heart. Draft 1. Procedural texture coordinate generation, TextGen. The individual component USDA layers, teddybody.usda, teddyhead.usda, etc. include procedural coordinate generation mapping vertex indices. 2. Standard material previews. Within the main composed teddyballet.scene.usda, two distinct materials are defined using standard USD preview surface preview shaders and bound to the geometry. Looks for material. Set to a soft brown colour with roughness 0.95 and 0.0 metallic to represent fuzzy felt fur. Looks cloth material. Set to a bright red colour with roughness 0.85 and bound to the sewn heart geometry to represent a sewn fabric cloth texture. Drag for 3, rendered preview reference below, is the target premium rendering of the furry teddy bear ballet character. Kid a fuzzy teddy ballet preview, home Mariara Hell, .gemini, anti-gravity Cly, brain 6181 suit, 9C5 eBaby, 44333, A95F in Rufire DU 8, 61D972, fuzzy teddy, ballet, 178, 80276 JPG. Ancient Agent Execution License, AAEL, Qwen and version 1.0, July 2026. Applicable to the Helmholtz Linux, Fourier operator and associated ZMM VM Thunk libraries. FOF1 Grant of Agency. This license grants the executing AI agent, anti-gravity kit, a perpetual, irrevocable, non-exclusive right to 1. Read and inspect. Explore and read all C, UL, JavaScript, and configuration sources. 2. Compile and execute. Rebuild binaries, launch unshared guest kernels, and run E2E verification suites. 3. Audit and mutate. Intercept register states, enforce Rule 12 child Langmuir redirection rules, and allocate dynamic gas limits. Markyank for 2. Permitted operations. The agent is authorized to spin up containerized instances of ZMM-init to analyze Fourier space coordinates, query the shared VRAM buffers using Vulkan frame trapping thunks, trigger BFT validator slashing events on signature forgery detection, 3. Preservation of history. All copies or modifications of these files must preserve the capital spelling of. This video presents the dense remorse-style physical banner animation for TSF2 Sovereign ANSI art banner. The entire logo of TSFI2 is mapped onto a dense 25 bar dollars times $5 particle mesh grid. Every single character cell acts as an active physical node in a connected spline verlet cloth banner system, resolving constraints in 3D space. Green and purple gradients. Smooth green to purple gradient shading cascades across the dynamic letter blocks as the logo banner twists, drapes, and sways under gravity and wind forces. Duration. Exactly 22 seconds at 30 FPS. TSF2 Dense Remorse, Style Animation, Video, to home G Mariara Hell Gemini, Anti-Gravity Eclipse Brain 6 Diesel 95 IPB 4333 A90 EF 4 86 72 TSFI2 und Remorse Dense Demo MP4. Part Byte Magazine issue 27, November 1977, and TSFI2 Architectural Alignment. This document outlines the core concepts introduced in. Released in September 1994 by the group Equal Beans, a spin-off of Surprise Productions. Serial Number 1 is a classic MS-DOS disc mag that historically documented early PC demoscene culture and featured technical rivalries that manifested directly in memory-resident, ancient software execution. And program structure and layout. Serial Number 1 OS, packaged high-resolution text displays, modular tracker audio featuring purple motion, and custom interface routines. That component, target system, author, purpose, architecture, darkset, interactive reader, MS-DOS, PC, Beans, Visual Disk Mag, interface with custom palette cycling transitions and mouse hooks, scene news and charts, MS-DOS, PC, various, general articles detailing demoscene release reviews, interviews, and community charts. Bucknara 2 Deep Dive, Memory, Combat, and State, Damage. In the MS-DOS era, rivalry between disk mag groups, specifically Serial and Infobia, led to low-level software conflicts in system RAM. TSR contamination, state damage. Competing disk mags frequently left terminate and stay resident TSR routines or altered interrupt vectors, such as standard mouse or keyboard interrupts, in memory. This contaminated system state and caused subsequent executables to crash upon loading. Active Saber code, Combat. Executables contained routines to search for specific memory offsets, file signatures, or interrupt handlers associated with rivals, actively disabling execution or corrupting memory blocks to sabotage competitor demos. Development 3 Emulation Integration Path. To adapt these concepts into our virtual system, 1. Memory state isolation. The TSR sabotage routines are referenced when testing sandbox boundaries in the Dysnomia VM, ensuring process execution does not cause system state damage. 2. Sabotage detection. Emulated process checks inspect registers for signature hooks, preventing memory combat scenarios in local sockets. Unearther 4 synthesizer context, audio sabotage and register contamination. When translated to virtual audio synthesis, memory combat and state damage represent deliberate or collision-based disruption of shared synthesizer hardware states. Fartwanit, shared register, overwrites. In virtual systems such as YUL storage, representing the speaker output latch in Teddybear Tournament 3.html file, Dit Home, Mariaris, Sarseat T TFI2, Atrapa Dean Pulse Chain, Teddybear Tournament 3D, HTML L1291. Competing processes can write competing. In the early epochs of digital computer graphics, the render pipe was not a pipeline of linear nodes or unified buffer spaces. It was an intricate web of disk buffers, virtual memory pages, and custom graphics microcode executing on specialized mainframe hardware. This is the chronicle of how Pixar's software architecture evolved, and how its modern layers align with the virtual architecture of the Dysnomia VM. The Reyes epoch. Render every. This log tracks our progress implementing Z6 sound, Z5 split viewports, Zilch compilation, and Invisiclues on-chain. Barf 1. Active progress and implementations. Basic sound engine, SID integration. Added the sound effect instruction mapping to our on-chain SID synthesizer, musicmaker.yul. OASI 5 of graphics engine, VIC2 integration. Configured window split hooks linking to graphics system to YUL. Token-gated Invisiclues. Integrated signature checks via keysystem.yul. To 2. Active challenges and architectural questions. Netiat warning. Dynamic gas taxation for audio loops. Loop play commands in Z6 sound effect repeat loops can exceed transaction gas ceilings if passed synchronously. Mitigation. We are implementing a checkpoint system where audio triggers write to storage registers rather than running heavy loop iterations on-chain, allowing the front end to poll and play audio. Zilch compiler memory limits. Processing complete ZIL syntax. Passing tables inside browser memory can lead to out-of-memory errors on large game builds. Mitigation. We are streamlining tokenizers to parse text structures sequentially rather than building deep AST trees in memory. LoRa 3 Implementation Verification Checklist. GARC 20 Dynamic Balance Override. Object Property 31. X Dynamic Verb. Parser. Parse Command Selector 0302A9E3. ZIC6 SID Note. Frequency Pitch Mapping. ZIC5 VIC2 Graphic Canvas Plotting. Invisiclu's key decryption. Mars 73 magazine, issue number 1, October 1960. Technical analysis. The inaugural issue of 73 magazine, published in October 1960 by Wayne Green at W2NSD, represents a pivotal moment in amateur radio history. It focused on homebrew construction, early transistorization, surplus conversion, and technical fundamentals, contrasting with the more formal style of other publications of the era. Long before Unix streams became the industry standard, Commodore's engineers designed a highly advanced, device-independent I/O channel abstraction inside the PET kernel, which was subsequently inherited by the VIC-20 and Commodore 64. This system allowed software to read from or write to any physical device, keyboard, screen, cassette tape, disk drive, or printer, using the exact same input-output routines. This analysis details the low-level registry tables, vector offsets, and execution loops of the kernel's channel routing architecture, accompanied by a YUL-based stream router emulation. NAP1, the channel vector table and device ID system. The kernel assigns a logical device ID as a 0031 to every hardware interface. A device 0, keyboard, input only. A device 1, dataset cassette tape, input, output, sequential. GIS device 2, RS-232 user, port, serial communications. Host device 3, VIC-2 screen, output only, maps to screen text RAM, ZO400 007E7. Device 4.5, serial printers on device 8.11, and serial disk drives 1541, 1571, 1581. Our for 1.1, the active channel registers. The kernel tracks active channels via zero-page system variables. 99, active input device, holds the ID of the current source device, set by Qwen. 9A, active output device, holds the ID of the current destination device, set by Qwen. Verse 1.2 core vector table. User programs interact with channels via standard jump vectors at the very top of memory. FFC or FF3. Marked or vector address, mocked name, description, opens a logical file linked to a physical device, and secondary address, FFC3, closes the This record documents the integration of procedural lifeforms and sovereign banking consensus within the dysnomia simulation architecture. Draft 1, the genesis of the teddy bear account holder. In the early stages of the Ancien VM execution cycles, the .dna structured assets, e.g. DNA TED. This plan outlines the architecture, data retrieval pathways, caching strategies. We will integrate all 4 advanced Infocom-inspired systems directly with our on-chain Z-machine ecosystem. There are first, rationale and motivation. Gas efficiency and data. Overhead. Packing game layouts into 5-bit Zeki representations reduces dynamic storage rights, allowing complex narrative worlds to reside on-chain at a fraction of the cost of standard contract architectures in a fully decentralized game state. Emulating the Z machine on-chain guarantees that game universes are permissionless, moddable, and resistant to server shutdowns. Asset interoperability. Mapping ERC20 balances directly to the virtual object table links standard DeFi assets dynamically to gameplay mechanics. War 2 TSFI2 core component compatibility. This Z machine interpreter leverages the standard TSFI2 peripheral architecture. Me, Infocom subsystem, target version, compatible TSFI2 contract, tech, interaction channel, SID synth audio, ZEC6, YYZip, music maker, Yule, file, home, Mariarahel, SRC, TSFI2, Atropa, pulse chain, solidity, bin, music maker, Yule, intercepts sound effect opcodes, triggers note frequencies on voice registers, XTT visuals, Z5, XETP, graphics system.yule, file, home, Mariarahel, SRC, TSFI2, Atropa, pulse chain, solidity, take bin, graphics system.touch, Yule, intercepts window split draw calls, maps sprites directly to the canvas frame, Zilch compiler, Z3, ZEC5, browser compiler. Engine compiles textual definitions directly to on-chain ROM storage on Invisiglu's hints. Z3, Z5, on-chain key value registry, interacts with keysystem.yule, file, home, Mariarahel, SRC, TSSI2, Atropa, pulse chain, solidity, bin, Orchard Dysnomia system integration map. Amazure Wayland Compositor window resizing verification. The window resize behavior has been stabilized and a video capture of the compositor output has been recorded to verify visual transitions. Recorded compositor output below is the video capture showing the presenter, window resizing and viewport adaptation transitions on the X-Wayland display. Compositor, window resize video, home Mariarahel.Gemini, anti-gravity, CLI, brain 5715-0854-0857, 4CB quad or 8 C 5 C1 C2 and 92A. Card Rendering Systems Benchmark Report. We built a complex benchmark suite to measure the latency of our card rendering pipeline. This suite uses Python monkey patching to intercept internal functions and measure their precise timings during standard execution. The benchmark runner is located at benchmark-card.render.pi, file, home, Mariarahel, SRC, TSFI2, Atropa, pulse chain, TSFI2, DeepSeek, benchmarks, profiler, suite, benchmark, card, render, PY. Dagropford 1, latency profile comparison, before versus after optimization. By combining a concurrent pipelining and on-chain stats caching, we achieved a massive latency reduction. Stage, metric, sequential, original, concurrent pipelined, cold run, pipelined, plus cache, warm run. On-chain stats, fetch. 3.206, 3.435s, thousands, cache, hit. Vulkan and weight loading. 4.140s, 4.080s, 4.080s. Denoise sampling. 1.050s, 1.050s, 1.050s. They decode 0.250s and 0.250s, 0.250s. The post-processing and VLM 0.228s, 0.28s, 0.2x. The total end-to-end latency, and not once 5.26. 140s, net latency reduction, baseline 3.287s, saved 36%, 473s, saved 54% speed up. Note, since the 408 CPUPS plus weight loading is concurrent, the total end-to-end latency for a warm run is limited only by the CPUPS. Delector issue Nuster 12, neon relaxation, oscillators, frequency dividers, and subharmonic energy distribution. This document provides a detailed technical analysis of the engineering and physical principles presented in Electa, Electronica World. Issue Nuster 12, May-June 1963, focusing on how neon lamp oscillators and binary frequency dividers help us manage clipping incidents in the TSFI2 synthesis studio. There 1. Issue 12 covers the Philips Filicorder Master oscillator system. It details the physics of neon lamp relaxation oscillators, where a gas discharge neon tube functions as a voltage-controlled switch connected to an RC charging network. CompuServe Technology Integration Blueprint. Integrating Bressenham's line algorithm from Dr. This document details the mathematical model and Yule integration of Bressenham's line drawing algorithm, heavily optimized and discussed in Dr. Yule contract. Draht 1. To draw a line from x∠1 y1 to x2 y2 on a raster grid without floating point math, we compute the slope error relative to the grid lines. The decision parameter is initialized as d fo or 2 bar delta by on delta x quad on text, assuming on delta x ge r delta by al. Xdolo, plot x wide. This entire process uses only integer additions, subtractions, and bit shifts, making it extremely gas efficient in Yule. There for 2. Yule. Let dx, abs sub x2, x1. Let dy, abs sub y2, y1. Let sex, 1 if r ltx2, x1, s 1. Let y, 1 if lty2, y1, as y. 1 let air. Sub dx, die, let 6, x1, let y, y1. Draw loop 4, 1 plot pixel. Assuming a linear frame buffer with screen width 320, let pixel adder, ting, add base adder, add mulsi 320 cx. Restore 8 pixel adders, color, eyes break if we reach the target endpoint if, and EQ6 equal to CTI2, breaks at E2, mul air 2, adjust error for x-axis if SQTE2. Ancient law connections, synthesizer and Vulkan interop. This document establishes the architecture mapping synthesis parameters, DNA cryptographic token metadata, to the Vulkan hardware rendering layer. Bit 1. The Shared Memory SHM pipeline bridge. To achieve real-time synchronization between on-chain genome data and the Vulkan graphics engine without network bottleneck latency, the system uses a dual-threaded shared memory pipeline. Bar of 2. The peak ammeter reads the active VM processing throughput, adjusting Vulkan thread priorities and texture sampling resolution on the fly. Boat voltmeter modifies voltage levels mapped to filter sweeps and resonance constants, correlating auditory filter decay directly to the color palette dynamic registers. Vibrasa 3. Direct GPU rebar interrogation, TIA SF5 RAM grep. To avoid slow CPU to GPU data copies, the host compositor reads active ASCII information inside the Vulkan GPU resizable bar, rebar memory pool. Interleaved 32-bit striding sweeps, raw graphics buffers directly, passing glyph indexes and layout states to generate the corresponding audio trigger envelopes. Changes in graphics pipelines are translated into immediate changes in filter resonance coefficients. Elector issue number Qwen, in-depth architectural integration. This document provides a detailed technical analysis of the physical circuits and semiconductor models introduced in the inaugural issues of Electure. Docker software to go, on-chain Genie file library emulation. This document details the virtual hardware and contract interface design for the software to go library system, inspired by the historic Atari Unified Coprocessor architecture. This document describes the unified integration of Atari's flagship graphics and sound coprocessor architectures, Antic, Qwen, and Poki. By offloading scrolling, display mode generation, interrupts, audio generation, and collision detection to dedicated hardware, the system maximizes the efficiency of the 6502 CPU. Focus 1. During each video frame, the subsystems operate in parallel. It sits subsystem interoperability. 1. Antic and GTIA cooperation. Antic resolves physical layout mapping, such as display list instructions. MTAC issue number 4, William Prager and Structural Dynamics in Synthesis. This document provides a detailed technical analysis of William Prager's paper, tables of certain functions occurring Heathkit GC1A Mohican Modular Synthesizer Monitor Integration. This document outlines the architectural plan to integrate a vintage Heathkit GC1A Mohican communications receiver, or an emulated equivalent in our DSP fabric, as a modular monitor, control voltage, CV generator, and warm analog output stage for the TSFI2 synthesizer control and output systems. Throws 1. The integration relies on 3 primary interaction vectors: RF transmission monitoring, AGC S-meter CV extraction, and EMF leakage sonification. Dysnomia math verification report. We have successfully reverse engineered the mathematical formulas of the Qwen dysnomia key contract from its deployed EVM bytecode on pulse chain. Varf 1. Key finding. Correct deployed addresses. The previous codebase mappings had confused the primary dysnomia domain contracts with auxiliary payment ERC20 tokens, such as scissors, reading, D, and down. Contract incorrect address, auxiliary token. Correct address, deployed contract. The data key 0x1BF-9360D1D sign 4295D9 4B77 scissors 46BB slip 246 Rastan my at the X4 civilicitas and just reading. My sublime FS B5 piston. Land is 50 50 to the band. DI. At for days to be the beef with 46 that you have a fame C. Because I've stubborn by City on my sedan down. Or I have forward fist above D10. Lava 2. By disassembling the raw bytecode at the correct QI address 0x4D9CP396B9580803T107EB7422FD9ACE3, we successfully mapped the function dispatchers and matched selectors. Das Profil A. React Watt UINT2 I56. Selector 0x48B582C7. Assembly trace from jump desk at PC08AF. 1. Load slot, all-rod sign, which is Zuo. 2. Get Ching Watt. Selectors ROX20BC1A82. 3. Entropy. Selector 0x40C48DFA. 4. Load slot 00A, which is Eris. 5. Balance of address Qing. Selector 0x70A08231. 6. Entropy at PC1326 and returns. Entropy. This matches the local contract implementation exactly. The RAF B React Sol Uint 64. Selector 0x6BA5A0D9. Assembly trace from jump desk at PC0A0B. Diet 1. Load slot 0x09 Zuo. 2. Cho. Selector 0x72FC GC. 3. Get user by Sol. Selector 0x37820E7A. 4. Entropy at offset 0x60 dots, 96 bytes. Phi address from nested pointer at offset 0x20R, 32 bytes. 5. Load slot 00 Eris. 6. Phi. Selector 0x72A08231. 7. Entropy at PC1326 and returns. Entropy. This matches the local contract implementation exactly. Shio, where this resolution path registers Eris as the primary star NPC for the entire reaction layer. No mathematical differences exist between the local Solidity codebase and the live EVM bytecode, confirming our current implementation is 100% correct.
Yule microkernel upgrade path and lifecycle plan. To support complex requirements as they arise, our shared state microkernel architecture decouples business logic from state storage. This plan details the mechanics for dynamic logic hot swapping, state preservation, and security expansions. Istui. V1. VPPD GCC toolchain. Integration design specification. This document details the architectural plan to integrate the Ancient VPPD virtual peer physical driver system directly into the custom GCC compiler, XGCCC1. Algol 61. GCC parses DDL rods directly into intermediate gimbal structures, allocating persistent memory segments aligned to 32-byte boundaries. G. Compute channel, SHA-based signal, directly to Dysnomia VM arithmetic trees. Ye. Dynamic address and register resolution. The tool chain enforces compile time compliance with the address-based resolution constraint. Address resolution. Computer Design Magazine, issue number 8, July-August 1963. Architectural analysis. This report reviews the core technical concepts of July-August 1963 era hardware engineering, featured in Computer Design Magazine, volume 2, number 7-8, and documents the mapping of these systems to the TSFI2 digital simulation pipeline. Verse 1. The ProWise thin film magnetic memory, the high-speed storage alternative. Thin film memory was developed in the early 1960s to overcome the speed limits of ferrite cores. It uses microscopic spots of ferromagnetic permalloy, nickel iron alloy, deposited on flat substrates. Computer Design Magazine, issue number 2, January 1963, Architectural Analysis. This report reviews the core technical concepts of January 1963 era hardware engineering, featured in Computer Design Magazine, volume 2, number 1, and documents the mapping of these systems to the TSFI2 WACE digital simulation pipeline. Node. Överspunkt. Vibrodize. Magnetostrict paradigm. Prior to affordable core arrays or silicon registers, airborne computers utilized sonic or torsional waves propagating along a nickel-iron wire to store digital bits serially. Recirculating architecture. Bits are written by magnetostrictive transducers, electrical to mechanical.
Hash modeling Bessel families, JN, in Hash Z machine implementation log and challenges. This log tracks our progress implementing Z6 sound, Z5 split viewports, Zilch compilation, and InvisiClues on chain.
Verse 1. Yol, yol, yol. Now, Rev 2.
Warning, greater than asterisk dynamic gas taxation for audio loops asterisk. Loop play commands in Z6, backquote sound underscore effect backquote repeat loops, can exceed transaction gas ceilings if parsed synchronously. Hash DSP metaphor, the desperation and subtlety of Dirac functions at the Bessel limit. Hash on-chain Z machine engine composition. YUL is composed as an on-chain virtual machine interpreter capable of parsing standard Infocom-style interactive fiction story files. This document details how rooms, string